Welcome to the module on applications of recycled batteries. In this module, we'll explore the sustainability of battery recycling and the open issues that must be addressed. Recovered materials from end-of-life batteries can be repurposed across multiple sectors, including the manufacture of new batteries, electronic parts, and other energy storage technologies. In many instances, recycling can impose a smaller environmental burden than producing metals through mining and ore processing. Metals such as cobalt, nickel, and lithium can be refined and fed back into battery production, while materials like graphite can be redirected into lubricants and other carbon-based products. Recovered fractions may also be used to produce ceramics, glass, and other industrial materials. Overall, this reuse both preserves natural resources and limits the environmental impacts tied to extracting and processing virgin feedstocks. However, despite numerous proposed pathways for replacing primary raw materials with secondary ones, there remains a substantial gap between research activity and real-world reuse at scale. This disconnect persists even though such secondary materials are often labeled sustainable because they originate from recycled waste. Consequently, any proposed recycling route should be assessed rigorously to confirm its true sustainability and practical value. Recycling plays a crucial role in reducing the environmental footprint of lithium-ion, lead-acid, and nickel-based batteries by recovering valuable materials, preventing hazardous waste release, and reducing dependence on virgin resource extraction. However, the environmental benefits and challenges of recycling vary across battery technologies. Lithium-ion battery recycling offers significant environmental advantages by recovering critical materials such as lithium, cobalt, nickel, manganese, copper, and aluminum. Compared to primary mining, recycling generally results in lower greenhouse gas emissions, reduced energy consumption, and decreased water use. It also prevents the release of toxic electrolytes and mitigates fire risks associated with improper disposal. However, current recycling processes, particularly pyrometallurgical and hydrometallurgical methods, can be energy-intensive and generate secondary waste streams, including slag, wastewater, and chemical residues. Improving process efficiency, adopting direct recycling approaches, and increasing collection rates are essential to maximize the environmental benefits of lithium-ion battery recycling. Lead-acid battery recycling is one of the most environmentally effective recycling systems, with recovery rates often exceeding 95%. Recycling prevents the release of lead and sulfuric acid into the environment, significantly reducing risks to human health and ecosystems. Recovered lead can be reused directly in new batteries with minimal loss in quality, greatly reducing the need for primary lead mining. Nevertheless, poorly regulated or informal recycling operations can cause severe soil, air, and water contamination. Strict environmental controls, worker protection measures, and regulatory oversight are therefore essential to ensure that lead-acid battery recycling delivers net environmental benefits. Nickel-based battery recycling, including nickel-cadmium and nickel-metal hydride batteries, helps mitigate environmental risks associated with heavy metals such as cadmium and nickel. Recycling prevents these toxic elements from entering landfills, where they could leach into soil and groundwater. The recovery of nickel and rare earth elements reduces energy consumption and emissions compared to primary extraction. However, recycling processes may involve chemical treatments that generate hazardous waste if not properly managed. Ensuring safe handling and effective waste treatment is critical to minimizing environmental impacts. In summary, battery recycling significantly reduces environmental pollution, conserves natural resources, and lowers the carbon footprint of energy storage technologies. To fully realize these benefits, advancements in recycling technologies, improved collection systems, and strong regulatory frameworks are required to support a sustainable and circular battery economy. Battery recycling plays an increasingly important role in improving the economic sustainability of energy storage technologies by recovering valuable materials and reducing reliance on primary raw material extraction. Lithium-ion battery recycling offers strong long-term economic potential due to the high value of critical materials such as lithium, cobalt, nickel, manganese, copper, and aluminum. Recovering these materials can reduce exposure to volatile raw material prices and supply chain risks. However, current recycling processes remain capital-intensive, with high costs associated with collection, transportation, disassembly, and complex processing. The economic viability of lithium-ion battery recycling is strongly influenced by battery chemistry, scale of operation, and metal market prices. Continued technological improvements, higher collection rates, and economies of scale are essential to improve profitability. Lead-acid battery recycling represents one of the most economically successful recycling systems worldwide. High recycling rates, often exceeding 95%, combined with well-established infrastructure and stable lead markets make the process highly cost-effective. Recovered lead can be reused directly in new batteries with minimal loss in quality, significantly reducing production costs compared to primary lead mining. The closed-loop nature of lead-acid battery recycling provides strong economic incentives for manufacturers and recyclers, making it a mature and profitable industry. Nickel-based battery recycling, including nickel-cadmium and nickel-metal hydride batteries, offers moderate economic benefits driven mainly by the recovery of nickel and, in some cases, rare earth elements. Recycling reduces dependence on energy-intensive primary extraction and helps mitigate disposal costs associated with hazardous materials such as cadmium. However, lower market volumes and variable material values can limit economic attractiveness. The profitability of nickel-based battery recycling depends on efficient processing, regulatory enforcement, and demand for recovered metals. In general, battery recycling can generate significant economic value by lowering raw material costs, reducing environmental liabilities, and supporting domestic supply chains. While lead-acid battery recycling is already economically robust, lithium-ion and nickel-based battery recycling require continued technological innovation, supportive policies, and market development to fully realize their economic potential within a circular battery economy. Batteries recycling faces system-level challenges across the full chain. Collection is still insufficient and battery diversity makes sorting and identification difficult, which can reduce recovery and increase safety and environmental risks. Disassembly remains labor-intensive and hazardous due to residual charge and flammability, while policy gaps and limited standardization hinder traceable, regulated recycling. Finally, many technologies are still scaling from lab, pilot to industrial operation, where consistent feedstock supply, automation, and validated emissions cost data are critical for sustainable deployment. In conclusion, battery recycling significantly reduces environmental pollution, conserves natural resources, and lowers the carbon footprint of energy storage technologies. Moreover, battery recycling can generate significant economic value by lowering raw material costs, reducing environmental liabilities, and supporting domestic supply chains. Finally, to achieve high recycling rates at a competitive cost and to meet the growing demand for batteries, significant innovation is needed in integrating existing recycling methods for batteries. This will require a collaborative effort from policymakers, researchers, and industry players to overcome the challenges and make recycling more efficient, safe, and sustainable. Thank you for your attention.